Let's solve a differential equation using Euler's method. So you can see my other video on Euler's method where I derive some of the theory, but for now we'll implement Euler's method and see how it goes. So to get started, let's give ourselves a little bit of a map for what we're going to do. So we'll solve the ODE, y prime equals f of t comma y. And let's tell ourselves some of the notation and initial conditions that we're going to use. So maybe something like y at t0 equals, say, y0. So this will be the initial condition, the initial theta. We'll also, let's solve it on the interval from t0 up to t, capital T, for a final time. Let's say with the Forward Euler or Explicit Euler method. Okay, great. So this gives us a little bit of a map of what we're trying to do and what our initial data will look like. And maybe we can say one more thing with step size dt. And n, or maybe it will be n plus 1 grid points. And we have a off by 1 error there often. So we'll think about that as we compute the time step. So to do this, let's start off with Lenzman arrays. So import numpy as np, and then we'll define Euler as, well, Euler needs to take in a few things. First of all, it needs to take in a function. It also needs the initial data, it needs the initial time, it needs the final time, what is capital T, and dt. Now, another possibility here would be to input the number of grid points you wanted. It doesn't really matter. For now, I'll code it as if we're putting in the number of, as if we're putting in the step size. Yeah, you can code it, you can try it the other way too, as you want. Once you have one of them, you should check what the other should be. So first, let's do that. So within the Euler function, we'll figure out the number of steps. Let's give ourselves a reminder for steps. And this will be n, it's equal to int of, we'll take the floor using numpy, so floor of the following. So we want to do something like t minus t0 divided by dt. That should be our number of steps. But, well, is that going to be the right number? And I think a good way to check this is just to write something down. So if, for instance, I wanted to do something like, I'll just kind of sketch this down here in the command line. Maybe I want just 3 steps, 0, 0.5, and 1, something like this. So that would mean that my time step, my dt, would be half, but I would have n equals 3 steps, right? So if I want my dt to be 0.5, and I take the interval from 1 minus 0, and divide by dt, then I get 2 steps. So that means, since I want 3 grid points, counting the beginning and the ending, I should add 1 to that. Of course, we don't want a decimal here, we want a floor. So, sorry, we want an integer, so that's why we're taking a floor. Okay, so then we will add 1 to this. I suppose this might be a little bit unnecessary to do both a floor and an int, but we'll keep it as is for now. All right, then let's define the time to be our initial time plus, and then we want something like, we want some type of array that looks like 0, and then the next step will be dt, and then the next step will be 2 times dt, and so on. It's kind of sketching this as I type. Notice we can factor a dt out of this. We're just doing a uniform time step for now. You could experiment with more advanced time steps. So we'll factor out something like that, and then we just want 0, 1, 2, so on, all the way up to n, something like this. To do that, it's tempting to use a range type function, but we need this thing to act like an array. So we'll use np dot a range. And I remember when I first saw this a range, I thought it stood for arrange. Arrange, the English word, has two R's. This has just the one, and it stands for array range. So just be careful about that. And we'll go here from 0 out to n. So that should give us what we need. Then, well, let's check if we do something like this. So if we go from 0 out to n, in our example above, we had n is equal to 3. So let's print this. And then we get 0, 1, 2. Let's see. Well, that is actually what we want. We want it to go, we want to have 3 different steps, and they'll be labeled 0, 1, and 2. So in this case, even though we have this, this is going to plus 1 here, this is going out to 3, this is giving us the numbers we wanted because we're starting there at 0. Okay, so, and if we wanted to, well, all right, so we've got something like that. After that, we need to initialize y. So what we would like to do is do something like y at n plus 1 is equal to y, is equal to y at n plus dt times a function, the function on the right-hand side, that's this function up here. And we want to evaluate that at t. But of course, t, we'll need the nth entry of t there and the nth entry of y. So we want something like this. If you check the standard Euler algorithm, this is the right update step. Of course, we need to put that in a for loop. So for n in range, range will go from 0 up to n minus 1, turns out to be sufficient. And then we need to indent this to get it inside of that for loop. All right. After that, we can return y, but it turns out it's also useful to return the value of t for plotting and things like that. Of course, this won't quite work because the first time it comes through, it won't know what y is, right? It'll try to access y at 0, and that won't be quite correct. Oh, by the way, you might guess why we're going here up to n minus 1. Well, that's because our very last value of lowercase n will be capital N minus 1, but then we'll have capital N plus 1 here, so this will fill in that very last value for us. So we need to initialize y first, and to do that, first we'll make just an array of zeros, so NumPy array of zeros, and we'll just have n of them. And after that, y at 0, so the first spot, we already know what this is. This is our initial data. So we need to use this initial data here that's being put into the function like this. Okay, so there we have it. We have a nice loop. So it comes in, it's going to compute how many time steps we need. It's going to compute the time vector, which can be pre-computed because this is just a uniform time step. It's going to create some space for our y variable to be stored in, initialize, and then step through all the iterations of the Euler loop. Okay, so what I'm going to do is save this and keep it in its own function. Notice that we haven't specified the f. This is just a generic solver. It has no idea what type of, what the ODE we're solving is or anything like that. It just does the computation. And this might seem a little bit annoying because we've had to keep things somewhat general, but it's pretty useful because now we can apply this to many different differential equations. We can call it in many different functions. We just have that Euler function sitting right there when we need it. So let's make a new script now, and this will just be something simple. Test the Euler dot. Let's maybe not even test it, but let's say plot outputs from Euler it's lowercase Euler dot m. Okay, so again, we'll import numpy as np, import, and so we want to plot this thing, so we'll import matplotlib dot pyplot as plt. And then from Euler, import, so from the script called Euler, we're going to import the function called Euler. And then what we'd like to do is take, and I like to go over here and take these outputs just as they are. So we would like to use these arguments to compute Euler, to compute an Euler solution. But for that, we need to tell what we need to tell Python what all of these different variables, what we want them to be. So we can do that something like this. First of all, the f, as it comes in, will just be, for now, we'll just make it a lambda function, seen in the previous video. So it's going to take in a t and a y. So maybe let's remind ourselves, maybe we'll make this a little bit more fancy. So plot solutions to the ODE. Maybe we'll say something like using outputs from Euler. Okay. So so now we have the form of the ODE right there. So first it's going to be a t, then a y. That's why we have this lambda function in this order, t comma y. And then let's try something like minus t times y squared. So that's our function, just f of t equals negative t times y squared. That's our ODE. So just to be clear, we are solving, right? Solve ODE, y prime is equal to minus t times y squared, like that. All right, with y t0 equals y. Okay, maybe overkill, but at least we know what's going on. So this f is now defined. We have f, and we can send it straight into our Euler function, and everything will be all right. We'll need to send in the other variables, but first let's not forget the outputs. So here, our outputs could be something like y and t coming out of Euler, and notice that that's exactly the order that these functions are returned in. So we need to keep the order here, but I might not want to keep the name. So for now, I might call this approx. So this is we know that the Euler equation gives us, the Euler algorithm gives us an approximate solution. So instead of calling it y, I'll call it y approx. And then each of these we can send in. So let's do something like y0 is equal to 1, t0 is equal to 0.0, final time, maybe 5.0. And for a time step, we can try something like 0.05, turns out to work okay. All right, so now we've just set up our function to solve. We now need to plot. So to do that, we can do something like plt.plot t comma y prox, and maybe we'll plot them with dash o's, something to that effect, and then plt.show open close parentheses. Okay, let's save that as Euler test, or maybe Euler plot.py. We'll test it later. That's why I'm making a distinction. Oh, we have, I need double quotes, I think should do it. And from Euler, import Euler. There we go. And we run it, we get something that looks like a curve, right? We're getting these dash O's in between. We could just plot it as a single curve if we wanted, or as a simple looking curve without the dash O by removing the O. But okay, that at least looks something like a solution to a differential equation, but how do we know it's right? And that's one of the biggest and maybe most important questions in scientific computing is, how do you know that your code is giving you what you think it's giving you? How do we know? I mean, just what is it? Do we just look at this and stare really hard and double check it in the book and things like that. What if we made a little error sometime? I mean, I intentionally don't go through and just show you a perfect script. You see me making little errors all the time. Any real coder will make errors as they code, but we'll know how to fix them or learn how to fix them. So let's see that as we go forward. So first, let's maybe make this a little bit nicer. PLT X label T. So I like to do this just because it's good practice to always label your plots. Something like this. PLT legend. So we haven't said what's going to go in the legend, but it turns out that we can do something like in that plot, we can give a legend label to that plot right now. So maybe something like label equals Euler approximation. Something that could be descriptive for the user. Okay, so let's take a look. And we get some labels on our plot. Euler approximation, you could add a title if you wanted to. But now let's do one more step, which is to plot the exact solution. So y exact, well, it turns out you can, this is this ODE right here is a separable ODE. So we learn in any basic ordinary differential equations class how to solve this, namely divide by y squared, integrate, and we'll go from there. Of course, not every differential equation is solvable, but I've intentionally chosen one with a nice solution. And with this initial condition, it turns out you can compute the exact solution fairly easily. And it turns out it's something like this. So, well, I want to make this a lambda function. It'll take in t, and it's 2. So I use 2.0 divided by 2.0 plus t squared. So you can double check that that is the exact solution to this equation. And you might say, well, why would we solve a differential equation if we can just find the exact solution? I agree with you. It's why numerically approximate the thing if we could just solve it exactly? Well, the idea is we can test on our code on things for which we know the solution, and then that gives us a greater degree of confidence when testing, when using our solver for things where we don't know what the exact solution is. And most differential equations can't be solved. For instance, I think if you even do something like replace this times by a plus, I don't know of a way off the top of my head to solve it, and I don't think there is one immediately. And if you don't like, if you did find some clever way to do it, well, guess what? I can put a 2.1. I think this will beat most methods, if not all methods. It's not hard to find differential equations that don't have known exact solutions. Okay, so with y exact coded in here, notice I can't just do something like plot y exact, because that's a lambda function. I need to plot the actual coordinates. So I'll do something like y exact of t. And notice, where's that t coming from? Well, the t is coming from the outputs that were computed by Euler, right? So going all the way back to the Euler code here, this line where we computed t is output by the function. And then we're evaluating the exact solution at those values right here. All right, and this is no longer an approximation. Maybe we should say this is exact solution. And I think I'm going to plot it without any label. You'll see why. If we run that, I'm sorry, without any decoration, I hope you can see okay. At least on my monitor, it looks fairly good. We've got the exact solution in blue there, and then in orange plotted on top of it, we see this orange type solution. I just want to point out, if I were to reverse these plots, of course I should be a little bit more careful, but if I reverse them, then the filled in circles kind of cover up. So first the blue plot is plotted, and then the orange one is plotted on top of that. Sometimes people see this and think that there's an error, like it's not showing the first plot, but it's just that the first plot is behind the second plot in some sense. So that's why I plotted them in the order that I did. So I would say visually this looks okay, but how do we know if it's actually doing a great job or maybe just an okay job. What is the degree of error? Well, one way to do that is to do something like look at the error of the difference between the two solutions. So to do something like that, maybe we could do subplot 1, 2, 1, and then after that, we'll do another subplot 1, 2, 2. And for this one, let's plot the difference between the two solutions. So y exact, y approx minus y exact. And this will be the error. If we plot this, we get a plot of the error. And you'll notice that the error is, well, it's okay, but it's not machine precision or anything like that. It's, we have maybe about about 2 decimal places of accuracy, something like that. This is something that's often left off when people are just getting used to scientific programming. They will look at a plot like the left and say, hey, that looks pretty good to my eye. Sometimes we call that the eyeball test. It looks good to the eye, and so great. That's we'll accept it. But it really depends on what you're trying to do. If the scientific instruments that you're using to measure things with already have an error that's maybe greater than this, you might not really care. This might be accurate enough for your purposes, in which case, great. However, if the if you have, say, very sensitive equipment, or you're dealing with a chaotic system, all of a sudden the being off by in the 3rd decimal place might really give you the wrong answer. So those errors can accumulate and amplify quickly in certain situations. So one really has to be careful and keep these in mind. Another point of looking at this kind of thing is to say, okay, well, this is the error based off a single choice of time step. What if I what if I want to have less error? Well, maybe one way to do that would be to cut the time step in half. So if we cut 0.05 in half, we get 0.25. And we see that the error is going down by about a half. And if one works through the theory of the Euler algorithm, you can see that this is exactly how it should cut down the error. If we divide again by 2, so in this case 0.0125, we see that the error gets cut approximately in half again. All right, so in the next video, we'll have a more systematic way of looking at these errors. So this is the kind of thing that we want we want to be able to work harder. So we're asking the computer to take more time steps, but we're getting a better result out of it. That is, we're getting a more accurate solution as we increase time steps. No numerical algorithm is perfect, but if we have something where we can increase accuracy by working harder, then we feel that we have some degree of confidence that our solutions will be believable. So thank you for your attention, and I'll see you on the next one.